I'm Tejaswini, and I'm going to be talking about how to use machine learning to optimize wireless networks, basically mobile networks performance on mobile apps. I work at Salesforce. I'm a data scientist working in the infrastructure division. And this particular technology was developed while at Twit Prime, which was a mobile performance startup. We got acquired by Salesforce in December 2016, and we're part of Salesforce since then. I'm going to be describing how exactly we modeled this problem, made it tractable, and devised a solution. My talk is kind of divided into 4 parts. First is I'm going to describe the problem, and then I'm going to talk about how we modeled it, and some examples from live traffic from this solution being deployed on different handsets around the United States, and some future extensions and implications of this technology. So let's talk about why is it important to optimize mobile networks for mobile app performance. Here are some statistics which kind of put this in perspective. Consumers on average, that is consumers like yourself and me, we spend around average of 3 hours a day on our mobile devices, and more than 85% of it is inside apps. And people are impatient. They want quick downloads, quick results. Close to half of the people remove the mobile app from their phone if it runs slowly. Close to 1/3 immediately look for alternate solutions if they weren't happy with the performance of a mobile app. So it's extremely important to optimize mobile apps for performance, for user experience and customer retention. One obvious way to do this is to do efficient software practices and to write good code. But another bottleneck in performance, which is not so obvious, is the wireless networking aspect. This kind of reflects in frustrations such as slow content download, your page getting stuck and you're not being able to see the content you're waiting for, etc. So we're trying to optimize the networking problem in mobile apps. So mobile networks are complex. This graphic kind of highlights why they're complex. So say I'm browsing the internet on my phone or using an internet-based app on my phone. There are so many factors behind the scenes which need to all work in sync for me to have a good experience viewing this content on my phone. We have like the network type, which could be either 4G, LTE, 3G, some Wi-Fi in a coffee shop, or it could be the carrier. Carriers that's another factor. Then the hotspots, the kind of API used in the app's code. A lot of them are third party. The CDN, the kind of device type, the OS on the device, and also a lot of apps have dynamic content, some have personalized content depending on the kind of app you're using, whether it's a social networking app or whether it's a shopping app. So mobile networks are complex, and yeah, a lot of things go behind this scene before when we're seamlessly browsing on our phones. So I'm going to give a high-level idea on how we solve this problem. So say this is the handset. Typically, when you download content, your handset sends a download request to an origin server or to a set of origin servers, which send the content back to your phone. We have added another level of servers in between the origin server and the handset. We call these accelerator servers. So the accelerator servers are more present in more geographies compared to the origin server. So what we do is we connect your mobile device to the closest and the best accelerated server to you, and we deal with the origin server from the accelerated server. So the leg from the origin server, the accelerated server is in the cloud, and this content transfer doesn't take a lot of time, and most of the optimization needs to be done between the accelerator server and the handset. Part of it is picking the right accelerator server, and the rest of it is optimizing for the many factors of variation which could affect performance while in the last mile. So our method optimizes TCP parameters for different combinations of apps, geographies, network types, access service networks, etc. So basically, when a phone has a download request, our accelerator server uses the best set of TCP parameters to maximize download throughput speed and a bunch of other download outcomes, given parameters such as the network type, the access service network, the device type, device model, etc. Our solution, we have tried to devise this without requiring any a priori information about the network or its quality. So it kind of learns this as our solution kind of learns the network and tries to optimize for it. We don't need to have any information about the network beforehand. And it's an iterative solution and hence adaptive. So we adjust TCP parameters as iterations go by, and hence it can also adjust itself if the network quality suddenly changes because of a lot of congestion, or if it also corrects for its mistakes. And we have the capacity to optimize multiple parameters simultaneously. Currently, we're looking at parameters which represent congestion control and concurrent connections. So before we go any further, I just wanted to talk a little more about what affects performance in the last mile. The last mile is between the final server and the phone. That's also called the network edge. We have many device models, many service providers, network technologies, Salesforce, cell towers, hotspots, signal variations, and all of that. So it's kind of like a combinatorial problem to know how to optimize what, and a lot of these things change with time, such as signal variations and network quality. So we have many permutations of factors which can change with time and which affect performance in real time. So it's pretty hard to predict what is really affecting performance at a given time, and also to figure out how to devise strategies which adapt with time and which help maximize your mobile performance on the network. So before we talk about how we devise this as a machine learning problem, I wanted to go into some of the modeling challenges we face and also what the data looks like. So the solution makes more sense. So the data we have are network requests logs data. So this consists of many fields. It consists of some IDs which correspond to the request ID and the session which the request existed in. And it consists, we also collect information about the phone or the device, which is device type, the OS on the device, etc. We collect information about the network type, the carrier, the access service network, which is being used. We collect information about the accelerator location, which the phone which the device has connected to. We collect TCP parameters which are corresponding to this particular download. And we also collect information from the origin server to the accelerator server, as in the amount of time taken for that data transfer. We collect download outcomes. Download outcomes currently, which we're interested in, are speed throughput, time to complete the download, and time to download the first byte. And we also collect information about the content. So we don't collect the content directly, information about the content, which is basically the file size, kind of content, the content type, whether it's a JSON or whether it's an image or what kind of content it is. So we collect a lot of data which is representative of the particular download which happens. The other modeling challenge we have is that, like a lot of machine learning problems, we don't have ground truth because network quality changes with time. So we can't optimize for a particular data set collected at a particular point in time because it may not translate to what's going to happen in the future. So this kind of makes it difficult for us to use supervised methods the way it is. This data is time varying and stochastic, which I just mentioned. And so it's also kind of, for this particular data set, it's kind of non-trivial to make any assumptions on structure. So we cannot put sparsity priors and stuff like that. Also, download outcomes such as speed throughput, time to download first byte, and download time, they have large variance and they're difficult to model probabilistically. Just to give an illustration of what I mean, I've basically taken the time to download the first byte for for two conditions. The first is a Wi-Fi network in Western Europe on an EOS server, and the other is an LTE network in the United States. And both of these are histograms and probability distributions for the time to download the first byte, and they are shaped differently. So it's also difficult. This kind of, if I add like more combinations, we'll see more variations on how this distribution even looks. So it's kind of difficult to decide that okay, we can decide a particular family of exponential distributions and estimate parameters because it changes so much. So I'll go over some design details which we introduced in order to design our final solution. So we tried to overcome the no ground truth challenge by randomly assigning a fraction of requests at every given point in time to bypass or control. So bypass traffic of the network and the data flow directly from the phone to the origin server. So this is what the download would have been if we did not introduce our layer of accelerator servers in the middle. And the other fraction is assigned to accelerated servers. So this is our solution to improve mobile performance. So basically at every point in time, we have a small fraction of download requests which download content like it would have if we did not intervene, and the other fraction uses our solution. So at every point in time, we want to know that we're doing better than bypass. That's our method of performance evaluation. And performance at any given point in time is measured by the accelerated. It's kind of like an error function, accelerated minus bypass divided by bypass, where the quantities can be any of these three download outcomes. It's time to download the first byte, completing the download, and the download throughput. We use aggregated quantities to measure this at any given point in time. Our solution runs over multiple iterations, and we eventually ended up remodeling this as a supervised learning problem. So what we do is we call it parameter exploration. So this is the only part where we are actually using human domain knowledge. So what we're doing is we define a polytope in the parameter space, which is a function of acceptable ranges for various TCP parameters. So let me just give you an example. Supposing we are looking at two TCP parameters. One is burst size, which affects congestion control, and the other is number of concurrent connections. So we define the ranges for these two parameters based on what we think is acceptable, and any point in this space is going to be an acceptable point. And we assign a fraction of the network traffic, which is assigned to accelerated traffic, to sample uniformly from this polytope. And we use machine learning to pick the optimal point in this parameter space to optimize the performance, hopefully after n adaptive iterations. So there's another aspect I didn't go over yet, which is how to deal with the lack of ground truth, but I'll go over that in a future slide. So this is our learning architecture. It looks big, but I'll kind of try to make it simple. I'll be going over the boxes in blue. So just to start, supposing I have a mobile device over here, which comes with a particular timestamp, which just happens at a particular point in time, and it's parameterized by all these factors and more. Given these factors, my accelerator server is going to assign a bunch of TCP parameters to this download, which we believe will maximize the experience of this download. So let's talk about how this accelerator server comes up with these TCP parameters, which is what our solution is about. So there are two ways the accelerator server can come up with parameters. One is through parameter exploration, which is what I just explained earlier. We are sampling parameters from a polytope uniformly. And the other is through some sort of learning. So we have an SQL database which collects all network requests until before this request happened, and we transform that from the network request space to a data matrix space, which I will go over in the next slide. So the data matrix space is basically a more easy space to work with, and we pass the matrix to a module which we call the policy module, and for every given iteration, we either run a Bayesian learning on it or we calculate the best parameters deterministically. So these happen in tandem. The Bayesian learning is called for more number of iterations than the calculate best parameters module. And the output of this is optimized set of TCP parameters. And we pass this back to the accelerator server, and the accelerator server gives a portion of the accelerated traffic parameters from the exploration and portion of the accelerated traffic parameters from the learning. So let's talk about how we generate this data matrix per iteration. So the design of this, we've kind of made it calculate at every iteration, and at every iteration it's representative of the real world network traffic this framework is optimizing for. So supposing in the real world we're having most of our traffic from a particular phone type or a particular access service network, or most of them is Wi-Fi, or most of them have a content size in a particular bucket. So this reflects that. And given quantities of interest, which is content type, phone type, etc., and a particular set of TCP parameters, outcome gains are calculated for every row in this data matrix. Outcome gains are calculated the way I described earlier, and these are calculated against the bypass samples. So every row consists of different permutations of all the quantities of interest. So this is what we call data matrix or a training set, which gets generated at every iteration. So I'll talk about how we do the learning right now. So our network, so our download outcomes, which is our speed throughput and our download times, they are a function of the network parameters. But we've kind of modeled this as an inverse problem. So we are considering our network parameter to be an inverse function of some function of the speed throughput and some function of the download times. And once we have this function, we set F inverse to be linear so that it can be used with linear models. This is just for convenience. And you can use some sort of a loss function, and that can be easily used with any kind of supervised learning algorithm. This is how we convert it to a supervised learning algorithm. And at every point in time, we estimate the best network parameter given we have a performance improvement. That's an argmin, sorry, it's a convex function, so I should have made it argmin. So yeah, and this is any predictive modeling loss function, which could be, a regression, support vector regressor, etc., or classifier, depending on that. So this in effect is, finding the best parameter which maximizes some loss function, and then we calculate the posteriori probability of throughput gain and reduction, and we basically evaluate this parameter. There's a posteriori probability that given this optimal network parameter, we are having a performance gain. So first we identify a probability of the best network parameter given that we want a performance gain, and then we calculate probability of a performance gain given this optimized network parameter. And then we check the posteriori probability and put a threshold on it. So supposing this is like less than a certain value, we don't use this particular generated parameter for our future download. So we just skip to the next iteration. And if it's greater than a certain value, say 60% or something, we have good confidence on the value, then we set our traffic share proportional to this. This is our Bayesian learning module. We haven't used any prior probabilities here because we try to not use domain knowledge about the network. And our helper module, which is the best parameters module, I'll first go over what we do. So here we design an objective function, which is a function of various outcomes, such as congestion timeouts, number of packets lost, number of packets sent multiple times, speed throughput, time to download the first byte, etc. So we designed some sort of objective function, and we find the parameter at every point which minimizes this objective function. And why we use this is twofold. The first easy to understand reason is to check performance of the framework. So if our Bayesian learning model is doing the right thing, then supposing at time t, we generate a set of TCP parameters from the Bayesian learning module. At some time t plus k, this best parameters helper module should return the same, should return a set of TCP parameters which are close to the Bayesian learning. So we kind of know that our framework is performing well, because in addition to being always better than the bypass traffic, we also need to know that we are ourselves getting the best parameters possible in the parameter space. And also, we want to reduce the number of iterations taken for finding the optimal TCP parameters. So including this helper module every n iterations will increase the traffic share for those parameters which are global maxima. So it helps guide the framework towards better parameter choices faster than otherwise. So I'll go over some sample results. This table is a very simple table. We picked a US retailer on their major US retailer on their LTE network, and used around 500,000 download requests over a week sent to one of their East Coast servers. We assigned around 10% of this to bypass, and for every bucket of file size, so these file sizes were calculated dynamically by clustering on the data for this particular US retailer. At every point, we have a gain over bypass. So the framework kind of works overall. I'll go into some more specific results which will show exactly how the learning framework works. Okay, so we picked a major US retailer for 2 weeks of time. The accelerator server is in central US on an LTE network based in where all the requests were based in Chicago. The size buckets were calculated dynamically using k-means clustering on file size. And this is week 40 and 41 and 42. Exploration, best parameter module, and learning are the three things I explained earlier. And let's talk about the first file size bucket, which is 14 kilobytes to 45 kilobytes. Our columns are the median speed, median download time. We are interested in these columns, which is the percentage of throughput gain, percentage of download, sorry, I don't know what I did. Yeah, percentage of throughput gain and percentage of download complete time. And for every row, we have like significant number of download requests, so the results make sense. What we see is at week 41, we didn't reach enough good posteriori probabilities for the learning to output a set of TCP parameters. But in week 42, the learning did catch up to produce some sort of solution. And the gain throughput by our Bayesian learning module is higher than the exploration, which is like, randomly picking from the parameter space. And also it's higher than the best parameter module. And we see the same thing for download. So a positive value for download for speed throughput and a negative value for download complete time mean that we're doing better than baseline or better than the others. So we see this for this bucket of file size. We also see something very similar for like file sizes of greater than 45 KB, where it took, by the second week, we had good Bayesian learning estimates to produce a higher gain than picking parameters at random. And we also see the same thing for small file sizes. I would like to also make a small comment that at all points in time, we're doing better than, than plain bypass samples. And we had around 1 million requests, close to 949,000 requests for this particular set of results. And I'll go over another set of results, which is the same US retailer for the New York, for the cell phones and the New York geography. And we see something very similar for the first file size bucket. We start off doing worse than bypass, but by week 2, we are picking good Bayesian parameter estimates to do better than both random and bypass. And there is a slight difference in the result for small sizes here, but I believe it kind of, for the most part, works, and it picks up as the weeks as the next week goes by. This won't have the final figures. So these are some representative results, and give some concluding notes. Our Bayesian learning module does not use prior probability terms because we try to optimize this without a priori network information, but our architecture allows for that addition of domain knowledge. We have exploited that yet. That is possible future work. And we also extended this framework to dynamically identify important data segments which need custom optimization. So currently, we are generating TCP parameters per accelerator server, app ID, and network type. But supposing we realize that there is another data segment in this, say, access service network, which needs custom optimization as well, we can dynamically identify this, and we can provide separate custom optimizations for each of these data segments as well. And this could lead to more customized estimates. So, and yeah, we kind of have a solution which we deployed in real world to solve this problem of, optimizing wireless networks using data and machine learning. I hope you enjoyed this talk, and just also share my email address in case you have any specific questions on our methodology or technology. Please feel free to email me. Thank you so much for being here.